Hi, my name is Kevin. I'm from Group 4. Today, me and my group members will be presenting about Experiment 6, which is torsion of bar. So, our group members, me, myself, Kevin, Afiq, Danial, Ahmad ZAKI, and Muhammad Abdullah. To begin this presentation, I'll be presenting about the introduction and objective of this experiment. So, torsion is a type of deformation which is a twisting of an object caused by a moment acting about the object's longitudinal axis. A moment which tend to cause twisting is called a torque. Torsion experiment involve the twisting of a sample along an axis and is a useful test for acquiring information like torsional shear stress, maximum torque, shear modulus, and breaking angle of material on the interface between two materials. Torsion bar rod or bar that resists twisting and has a strong tendency to return to its original position when twisted. So the main objective of this experiment is to investigate the relationship between torque and the angle of twist theta of circular or rectangular cross-section bar. Another objective is to determine the modulus of rigidity of materials.
So next part is the theory of the experiment. So basically, it is a cylindrical rod that is attached at one end and has the other end twisted or torque is called a torsion bar. And the rotational angle referred to as the angle of twist can be calculated when the bar twists. And shear stress is the term for the stress that form as a result of the twisting. So the formula of the torque is equal to Fr sin theta, whereas F equal to perpendicular force applied, R equal to the radius of the rod, and theta is the angle between the force and object. We can get the shear stress equation from L multiplied by gamma equal to P theta, and we can get gamma equal to P theta divided by L. Whereas gamma is equal to the shearing strain, P is equal to length from center to any point in the circle shaft, theta is the angle of twist, and L length of shaft. The shaft or the rod surface experiences the most shearing strain, where P is equal to C. We can get gamma max equal to C theta divided by L, where gamma max is the maximum shearing strain, C radius of the shaft, theta is the angle of twist, L is the length of the shaft or rod. Since the stress generated is not exceeded anywhere inside the shaft, Hooke's law may be used to link shearing strain and shear stress in the elastic range, whereas the equation relationship is gamma max equal to torque max divided by G, which is the modulus of rigidity, is equal to Tc divided by Jg, whereas J is equal to the polar moment of inertia. Hence, the maximum shear stress can be found by equating both right-handed side of the equation. So we can get theta is equal to TL divided by Jg, whereas theta is equal to angle of twist, T is equal to torque exerted on shaft, L is the length of shaft, J is equal to polar moment of inertia, and G is equal to the modulus of rigidity.
So moving on, as for the experimental setup, we will need a torsion bar testing machine, steel rod, aluminum rod, nylon rod, load which is 1 Newton and 5 Newton, spanner, vernier caliper, and a ruler. So the material should be arranged as shown in the picture here.
Assalamualaikum. My name is Ahmad Zaki bin Majais. I will talk about methodology and safety procedure for this experiment. The first procedure for this experiment is the aluminium rod is clamped and the load hanger is placed in position. Then, the rotation scale is set at 445 mm from the fixed clamp, and also pointer is also set to 0 degree. A load of 10 Newton is added by 10 Newton increment each until 18 Newton, and the degree at the pointer is recorded in table 1. The load then removed and the rotation scale and pointer is set at 245 mm from the fixed clamp. Repeat the previous step for this leg. After done recording for the aluminium rod, we will change the specimen to steel rod and repeat the same procedure for the aluminium rod, and the result will be recorded at table 2. Finally, the nylon rod is clamped in position at also 445 mm and the pointer is fixed at 0 degree. A load of 1 Newton is added by 1 Newton increment until 5 Newton, and the degree at the pointer is recorded in table 3. The diameter of the rod in table, according to the type of material, was measured and recorded. There is 5 things that we need to take into the account in the safety procedure. The first one is, to avoid parallax error, keep your eyes perpendicular to the scale when taking the reading measurement. The second one is, ensure the rod used is not deformed. If it deformed, change it to the new one. To increase the accuracy, take the measurement reading when the load is not swinging. And the second last one is, to avoid load fall, make sure the hole is tightened before starting the experiment. And the last one is, ensure the student wear proper PPE when conducting the experiment, which is the lab coat.
Next is the calculation for the experiment. We are going to calculate the torque for each material used, which is the aluminum alloy rod, steel rod and nylon rod. By using the formula T is equal to Fr sin theta, whereas R equal to the radius of rod, F equal to the magnitude of force applied perpendicular to the rod, and theta is equal to angle between radius and force. So the first material used is the aluminum alloy rod. The torque for the rod length 445 mm is 1.13 Nm for the load 10 Newton and 5.561 Nm for the 20 Newton load. Whereas for the rod length 245 mm, the torque produced for the load 10 Newton is 1.13 Nm, and for the load 20 Newton, we get 4.450 Nm. Next is the steel rod. For the rod length 445 mm, the load for 10 Newton is, we can get the torque 0.432 Nm, and for the load 20 Newton, we can get the torque is equal to 3.453 Nm. Next, for the steel rod length 245 mm, the load 10 Newton, we get the torque 0.432 Nm, and the load 20 Newton, we get 1.728 Nm. Next, for the nylon rod length 445 mm, by using 1 Newton load, we get 0.507 Nm, and for the 2 Newton load, we get 1.347 Nm. For the nylon rod length 245 mm, the load 1 Newton, we get 0.113 Nm, and the 2 Newton load, we get 0.902 Nm. Next, we are going to calculate the modulus of rigidity. So first, we are going to find the polar moment of inertia, whereas J is equal to pi c power of 4 divided by 2, and c is equal to radius of rod. And then we can get the modulus of rigidity, whereas G is equal to L divided by mj, whereas L is the length of rod, J is the polar moment of inertia, and m is the value of slope from the graph. So these are the models of rigidity for aluminum alloy rod. So we are finding the polar moment of inertia for the length 445 mm, which is 152.72, and we get the length is equal to 445 mm, and the m, which is the gradient of the slope we get from the graph, is 0.20743, and calculate by using the formula of modulus of rigidity, we get 804.75 Newton per millimeter square. For the length of 245 mm, we get 477.43 Newton per millimeter square. So the average modulus of rigidity for aluminum alloy rod, we get 0.64 GPa. Next is the modulus of rigidity for steel rod. Same as the modulus of rigidity of aluminum rod, we find the J which is the polar moment of inertia, we get 58.9491, and the length is 445 millimeter, and the gradient from the graph is equal to 0.277, and we get the modulus of rigidity is equal to 1561.24 Newton per millimeter squared. And for the road length 245 millimeter, we get the modulus of rigidity 898.14 Newton per millimeter squared. And we find the average modulus of rigidity for the steel road, we get 1.23 GPa. Lastly, for the modulus of rigidity for nylon road, for the road length 145 mm, we find the J polar moment of inertia, which is 172.0574, and the length is equal to 145 mm. Next, we find the gradient M, we get 2.7628, and the modulus of rigidity is equal to 53.61 Newton per millimeter squared. And for the road length 245 mm, we get the modulus of rigidity is equal to 35.14 Newton per millimeter squared. And finally, the average modulus of rigidity of the nylon rod is equal to 0.0394 GPa.
Bismillah, Assalamualaikum. My name is Muhammad ABDULLAH bin Mukram, and I will explain to you about the discussion. So the discussion that we get, the data that we get is from the experiment that we have done it last week. So the first one is aluminium steel rod, and then you can see the aluminium alloy rod, and steel rod, and also nylon rod. So we can see that steel rod is more smaller in terms of twist of angle, and followed by aluminium rod, and lastly nylon rod. So next is basically this is the graph torque versus angle of twist. Then you can see that for the aluminium, steel, and nylon rod is basically they have the smallest gradient and also the smallest number of angle of twist. You can see that the gradient is very low, because the slope is not very steep compared to the other tools, which is metals that have very steep slope for the gradient. Next, I will discuss about the graph and the table at the next slide. The graph of angle of twist against torque of the aluminium rod, steel rod, and nylon rod are constructed and shown in Figure 1, Figure 2, and Figure 3. Based on the graph result obtained in this experiment, the angle of twist is directly proportional to the torque applied towards the material. It is also observed that every graph has a linear line where the torque increases, and from that the angle of twist steadily increases. Thus, the linear of the graph obtained indicates the materials to exhibit purely elastic behavior. By comparing the data obtained from the experiment, it is found that the experiment does not verify the torque over twist formula. Then random occurrences and systematic errors involved when conducting an experiment that can lead to the similarities of experiment result compared to the theoretical results. From the three graphs plotted as shown in Figure 1, Figure 2, and Figure 3, that the torque is directly proportional to the angle of twist, the angle of twist increases along with the torque. The length of the rod or other material will have an impact on the graph's slope. As we can see in each graph or for each specimen, the slope will become steeper as the length is reduced. The graph also demonstrated how different materials behave in a purely elastic manner, and how their properties will affect the angle of twisting. According to the graph that I have shown in the first slide, the angle of twist has an inverse relationship with rigidity modulus, which is G, and then a narrower angle of twist raising the rigidity modulus value. Next, on to comparison between three different materials. First, the choice of material is a critical factor in comparing aluminium, steel, and nylon bars, each with distinct properties. Aluminium is lightweight and corrosion resistant, and steel offers high strength and stiffness, and nylon is a non-metallic material known for wear resistance. Second is when assessing their torque versus twist behavior, it is evident that aluminium and steel bars exhibit linear relationship due to their stiffness, while nylon's non-metallic nature may lead to a more nonlinear response to torque. Third, the length of the rotation scale and pointer on each bar plays a role in the precision measurement. The longer the scales allow for more accurate tracking of twist angle during experimentation. Next, additionally, the torque range within which each material operates effectively varies, where steel being capable of withstanding higher torques compared to aluminium and nylon, making the selection of the appropriate material crucial for specific application experiments. By comparing these factors, you can make an informed decision about which material and length of bar is best suited for your specific application or experiment. Each material and length will have its advantages and limitations depending on the requirement of the task. From the experimental finding and result, it can be concluded that the relation between the modulus of rigidity of respective material is depending on the type of materials, such as size of atom, type of bond, characteristic of each materials, where it is effect. The experimental results plot and act as main objective of the experiment, where observations need to be done on different material to check torsion on different materials. For the length of the bar, which is calculated from fixed clamp, the relation can be made if the graph is decreasing proportional as the length is increased. The number twist of rod is decreasing coefficiently as the length. For the shape relationship, circle shape is used compared to square rod, as it is easier for the rod to twist smoothly. For the polar inertial moment itself, it is used to calculate the torsion of the inertial moment on a cylindrical object on a parallel plane to the object's central axis. It can be concluded that the polar inertial moment is increasing proportionally toward the modulus rigidity. It is reasonable to conclude that each of the three types of bar indicate a different number of twist rods, as indicated by the rotation scale based on the tabulation of data gathered during the experiment. It is clear from data table 1, 2, and 3 that there are various number of twist rods when compared to another. The tensile properties of each individual substances help to explain this. Due to the least increase in twisting when load is gradually added increment of 10 Newton, steel rod is the hardest and the strongest rod bar amongst the material. Nylon rod come in last, followed by aluminum rod in second. Result for nylon rods demonstrate that each additional load causes a significant amount of twisting. As a result, it can be said that nylon has a very low tensile strength. This comparison can also be explained in terms of chemical bonds, with nylon being covalent bonds, stainless steel being an ionic bond, and aluminium rod being a metallic bond, because they are packed tightly and strongly against one another. Metallically bound atoms are very tensile and difficult to break. Ionic bond is a strong primary bond as well, but because of the transfer of electron, it is more brittle and difficult to break. Finally, because the atoms only share a valence electron, covalent bonds are the weakest primary bonds in the group. It is a simple fracture and deformed. The material is also hard, not tensile, and weak. For the closing and the summary of discussion, the two lengths 245 mm and 445 mm were used in this experiment to compare the distance between indicators and the fixed clamp. The overall conclusion that can be drawn from the experiment is that the number of rod twisted decreases almost in half as the distance double. From 245 mm to 445 mm, we can therefore draw the conclusion that the number of rod twists decrease proportionally as the distance between the pointer and the fixed clamp increases. Then we can conclude that steel is the strongest material available and can withstand higher shear stress than the other two materials, thanks to its high rigidity modulus and applied torque at failure values. Among the three materials, aluminum alloy came in second place because it can withstand more ply and shear torque than nylon, but not as much torque as steel. Due to a material quality known as ductility, it can withstand greater angle of twist. The least rigid nylon rod demonstrate nylon's least ductile nature. these are our appendices where we have done our experiment. This is the proof that we exactly follow the exact procedure so that we can get this kind of data, and we can explain to you about our discussion, what we get from the experiment. So this is the proof, the appendices that we can provide in our report. That's all from me. Thank you.
Lastly, to conclude this experiment, we are needed to investigate the relationship between torque, the angle of twist theta of circular or rectangular cross-section bar, and to determine the modulus rigidity. All these have been determined throughout the experiment. We also found that the torque is directly proportional to the angle of twist of a circular cross-section specimen. So, in order to carry out this experiment, these are the references that we referred, and that's it from us. Thank you.